Okay, so yes, as one said, I'm a member of the LIGO-Virgo collaboration, and so today what I want to talk about is a kind of summary of a few works which will constitute my PhD thesis, more or less, which focus on how can we use black hole spectroscopy, so how can we harvest the coalescences of black holes to extract implications on fundamental physics. So okay, yeah. So I'm not sure how some of you are familiar with some of these topics, so I will give a brief introduction to how we describe gravitational waves from black hole mergers from a theoretical point of view, and to black hole perturbations. So we introduce the concept of quasi-normal modes and ring-down emission. Then I will give an overview of the main technique which I will use during the remainder of the talk, which is black hole spectroscopy, and precisely time domain black hole spectroscopy. And I will discuss the first black hole detection that we ever had, and it was also coincidentally the first time that we actually observed the ring down from a black hole. And then I will go on and apply this technique to 3 specific cases, which I hope would be of interest. So the first case is the background from okay, it's telling me that I have internet connection, so let me know if you're having troubles.
Yeah, I'm not listening all right.
You were gone for like a few seconds, yes.
Yeah, can you repeat the last minute?
Yes, I will try to stop my video and maybe this should improve. I'm sorry, this usually doesn't happen in the office, so I don't know what's wrong. Can you hear me all right now?
Yes, perfectly.
Okay, so yeah, let me know if it happens again. Okay, so yeah, I was saying that I will apply this technique to test the Bekenstein-Odd universal bound, which is a bound on the information emission rate of black holes. And finally, the third case, which I will analyze, is how we can constrain some candidates of dark matter by analyzing the ring down and including the effects described by the Kerr-Neumann metric. So black holes with charges. Yeah. So very briefly, I think you are all quite familiar with the fact that we now routinely observe binary black hole coalescences here on Earth. This is the first detection from the full network, so the 2 LIGO and the Virgo detector here near Pisa. And now so the first ones were kind of special, each one was special, but now we observe so many of them that we publish catalogs of these events, and you see that we also span a quite wide mass range from few solar masses black holes to hundreds of solar masses black holes. And so how do we describe these coalescences? So if you want to simplify the coalescence, you can split it into 3 main phases. So the first one is the in-spiral phase, which is essentially can be described as a quasi-adiabatic evolution. So the 2 objects are in-spiraling one with each other, and so essentially here the gravitational-wave emission timescale is slower than the orbital timescale. So you can describe this with what's called post-Newtonian theory. But then at a certain point, the radial momentum becomes increasingly important with respect to the orbital one. And so the 2 objects are strongly attracted to each other, and they plunge one onto the other and merge. So a common horizon forms. And this is a very highly dynamical regime where no satisfactory analytical technique can be used. There are some attempts, but none of them is really satisfactory. So you have to use numerical simulations to describe this phase. And finally, once the remnant object has formed, so a common horizon has formed, you have this highly distorted object, which then approaches equilibrium, so it sheds off all its anisotropies, and in doing so, it emits gravitational waves according to its normal modes. So it vibrates according to its normal modes, and specifically damped normal modes. And this phase, in its spectral content, can be described by perturbation theory. Now I will focus on specifically on Ringdown, and to understand what is Ringdown, you have to remember that space-time is a dynamical entity, and so this implies that it can undergo oscillations even when no matter is present. And the Ringdown is exactly this. So black holes are completely vacuum solutions, but they can still vibrate, and in vibrating, so they can vibrate, and specifically they can vibrate according to their own quasi-normal modes, which are excited when a black hole is perturbed. So the Ringdown is essentially the gravitational wave emission corresponding to the excitation of the normal modes of the black hole. These are damped both by the presence of the gravitational wave emission and of the horizon. So this sets specific boundary conditions which imply damping. But the key thing that you have to remember is that the spectrum is independent of the perturbation details. So the spectral content of this emission doesn't depend on how you perturb the black hole. So whatever you throw at the black hole, that doesn't change the spectral content. So it's a kind of space-time signature of the system. And an easy way to derive them is by linearizing Einstein equations on a black hole background. And so very briefly, what you do is that you take a background metric G bar, you add some small perturbation h mu nu, and upon changes of variable, you have to solve, this is the non-spinning case, which is the easy one. You have to solve this equation, which in the frequency domain is essentially equivalent to a Schrödinger equation with an effective potential, which I depicted here for a few moments. And so now I'm showing a numerical simulation, so simulation of what happens when you perform such a numerical experiment. So what I'm doing here is that I'm throwing a Gaussian packet onto the black hole, and the black hole here is represented just by the effective potential, and the horizon is at minus infinity. So what happens here is that you throw the Gaussian packet, the packet gets distorted. You see that even before getting to the black hole, the packet is distorted. This is an effect of the tail of the potential, so the long-range curvature of the space-time. Then part of the radiation gets absorbed by the black hole, and so it goes through the potential, and part of it gets re-emitted away. So the way you have to think about a black hole in this case is a filter. So you throw to the black hole whatever you like, and the black hole filters this perturbation according to its own fundamental frequencies, to its own normal modes, and re-emits a signal, which is a superposition of essentially constant frequency terms with a damping. So it's a damped sinusoid, essentially. And this translates into gravitational wave multiples in quite a simple form. So you simply have that the gravitational waves polarizations in this case are a superposition of constant frequency terms with a damping. And of course, there is some excitation factor, which depends on the specific configuration in which you excite the black hole. And the superposition is done in terms of two angular indices, Lm and the overtone index, so the higher harmonics. And it's quite similar to quantum mechanics, actually. And the key point here is that the frequencies and the damping times of the spectrum can be predicted by perturbation theory, and they are fixed only by two parameters, which are the mass and the spin of the black hole. This is a consequence of the famous Noether theorem, which tells you that the black hole is characterized only by these two parameters. And so you see, here you have a theoretically infinite number of parameters, which are the frequencies and the damping times, which you can measure, you can extract from the data. But then they are fixed only by two parameters. So this means that, for example, if you measure two frequencies and one damping time, you can have a test of general relativity, because you measure the first two frequencies, you invert them to find the mass and the spin, and then with the third independent measurement, you can now test the prediction of GR, because the third one is already predicted. Of course, in reality, things are a little bit more complicated, but this is the main idea which you should bring with you. And also, in some sense, it's interesting to test GR, this emission, because it's a kind of a simple prediction. Because it's just a superposition of constant frequency term and some damping. So it's kind of easy to incorporate beyond GR effects. Of course, there are complications, but it's still easier than in other phases of the coalescence. And finally, before going to showing you the results which we obtained by analyzing this phase, I want to ask a question, which is why should we use Ringdown to test gravity? Because that there are a lot of different ways and astronomical systems to test gravity. Why specifically gravitational waves and specifically Ringdown? So the first very important point, of course, is that this is the largest curvature regime. So the merger Ringdown is the largest curvature regime experimentally accessible. Which of course it's important, because if there is some modification to GR, we expect it to have it during this during the large curvature. This means that you can excite effects. Okay, my connection is stable again.
Yeah, you were gone again for a few seconds.
Okay, sorry, but
yeah, it was only 2 seconds. Don't worry.
Okay, yeah. So what I want to say is that it is a highly dynamical regime, which is very important to test effects like scalarization and descalarization in quadratic gravity, or in general any effects which arise only in the dynamical regime. And most importantly, this is a very useful tool, because you can gauge quite precisely the contribution of missing physics for precision tests. And for example, you know that stuff like cosmological expansion, dark matter, and most importantly, accretion, magnetic fields, electric charge, none of this is expected to play a role, at least in the LIGO-Virgo detection. Some of these effects could affect the signal for LISA, but for LIGO and Virgo observation, these are really not expected to have any effect, which of course is quite different, for example, from X-ray binaries, where you have to model the emission from the corona, etc., etc. And so, yeah, the summary is that gravitational wave Ringdown tests are clean, and there's a nice review by Barause, Cardoso, and Pani, which describes some of these effects. Okay, so now I will go straight to the observations. And this is the first observation of Ringdown we ever had. So it's 150914, the first black hole detected by the two LIGO detectors. On the right, you can see the reconstruction of the waveform, which I've taken from a subsequent analysis we did. And so you see the signal is just a damped sinusoid, essentially. So it's a quite simple form. And on the left, you can see the probability distribution on the frequency and the decay time. So you are seeing actually the 90% credible intervals. So the frequency, the damping time are constrained to be within these regions. So the black is the prediction from GR, and the dotted lines are the analysis done at different times. And you see that when you enter this linear Ringdown regime where your description is valid, you get a measurement which is consistent with the prediction of general relativity. And so, of course, this was an extraordinary achievement, and it sparked so much interest in the community. But of course, since it was the first time that Ringdown was observed, the initial techniques were quite simple in some way, of course, because you wanted to do in the most agnostic way possible. But then we of course, we wanted to refine this technique and improve it wherever possible. So the approach that we have taken in a subsequent paper with my supervisor, Walter Del Pozzo, and John Veitch, which is a professor at University of Glasgow, is to
sorry, Gregorio. Sorry.
Yes.
So can you go back and
yes.
So these times are really can you put them on the right hand side? Are there milliseconds?
Yes. So these are the difference.
They're really, yeah.
Sorry.
They're really between. So they're really in the blue part, no? In the.
Yes. Yeah. So it's essentially, okay, this is the real data deconstruction, so you cannot see it very well, but imagine that this is the peak of the emission, essentially, and then you are starting, for example, 1 millisecond later, 3 milliseconds later, or 6 milliseconds later. So okay. This would correspond to the differences between the peak of the emission and the time at which you start the analysis. So this specific analysis was started like 4 milliseconds later. So the difference between this peak and this start is 4 milliseconds, essentially.
I see. But the later you start, the more you enter the noise, no?
Yes, exactly. I bleached on this part, but yes, the point is that in principle you would like to start later because you are in the linear phase, But of course, these are an exponentially suppressed emission. So the later you start, the fainter the signal is. So you enter really the detector noise, and there's really no signal that you can extract.
I see,
That's
yeah.
why these curves they essentially widen the higher the start time is. So at 1 millisecond you have a very precise constraint, but then at 5 milliseconds you have something which is very large, and at 6 you lose completely information on the frequency.
Yeah, thank you. Thanks.
Okay. All right, so yeah. So the technical step that we did is to use what's called a time domain approach, which is important to avoid any spurious contribution from the previous phases of the coalescence, especially from the merger. And so here I will present results with this technique. Of course, there are a lot of technical details which I don't want to go into, but if you have any questions, please feel free to ask them. But so the easiest way in which you can do black hole spectroscopy, so the easiest way in which I'm going to explain it, is that you first perform an agnostic reconstruction of the frequency, which is represented by these blue dots and these black lines, which are the 50 and 90% contours. So essentially you just assume that there is a damped exponential in the data, and you extract the frequency and the damping time from that. So it's completely agnostic on the system. And then you impose the predictions coming from general relativity, and you predict the spectrum that you should have. And these are all these modes in the spectrum. All these colored ellipses represents all the different modes in the spectrum that you expect to have. And then you lay the agnostic prediction on top of this, and you can compute the probability that the recovered mode that you had in the agnostic way corresponds to a given predicted mode. And in this case, you see that we could not really distinguish between all the different modes because the reconstruction is so wide. But in the future, we expect to pinpoint precisely which mode you had. Of course, these are a very basic way in which you can do this. There are more refined way. And
hey, Gregorio,
yes.
Sorry, I think we missed you precisely when you were explaining the horizontal plots.
Yes. So okay. So the blue dots are diagnostic reconstruction. Yes. So the blue dots are diagnostic reconstruction of the frequency, and the black lines are the 50 and 90% contours on the reconstruction of the frequency. So this is the agnostic one. And then you essentially compute the prediction from GR, and you compute the probability that the agnostic mode that you recovered is exactly the one that was predicted by GR. And
so
yes.
Can I ask a question? So this theoretical prediction from GR that you make in the circle, so in the colorful contours, they assume some mass and spin, right? Because otherwise there is no prediction you can make.
Mm-hmm. Yes. So there are several ways you can do this. So this is computed assuming the full IMR emission, but of course, for example, once you measure two modes, you can imagine you measure two agnostic modes. You can then invert them to find some mass and spin and predict this spectrum with that. So there are several ways, several flavors in which you can do this. I just showed that, let's say, the basic one here. But
okay, thanks.
Yes. Yeah, you have to assume. You have to assume essentially the prediction of the spectrum as a function of the mass and the spin in order to be able to do this. Yes.
So can you explain which one of the colors? What are these numbers? What are the 3, 2, 3, 3, 1, or the P? What is the difference?
Yeah, sorry. So these numbers correspond essentially. So let me go back a couple of slides. So I showed you. Yeah, these numbers correspond to the angular indices, which I'm showing here. So the L equal 2 would be the quadrupolar mode, and the L equal 2, M equal 2 are the fundamental one. Right. The fundamental ones, and the N equal 0 would be essentially the harmonic. So I'm showing in this plot, I'm showing only the fundamental harmonics. Yeah. And so this L equal 2, so this green blue part of the spectrum is the dominant quadrupole, while the yellowish red part is the L equal 3 spectrum. And these are all the different M's coming here. And on the right, you can see the probability that you have identified each mode, essentially.
Okay. Thanks.
Yes. And so as I was saying, of course, this is a very basic way in which you can do this. And as a collaboration, we are clearly interested into doing this in a more imposing more information, so trying to extract more information from the data with a more refined model. And of course, that was on the first detection, but we wanted to do it on all of the detections. And so that's what we did in the recent catalog of in the recent catalog published by the LVC. So it's the testing GR catalog, where there was a catalog of Ringdown all the observations. And of course, in this catalog, we did many things. I won't go in detail through all of them. But for example, we searched for higher modes, so modes different from the L=2 and higher overtones, etc. And we also computed what's called Bayes factor, which is a quantification of the evidence for the presence of higher modes, or in general for the presence of any modifications in the GR spectrum. So yeah, I'm not going into details here, but I just want to bring with you a message, which is that just much more than 15914 when it comes to Ringdown. So because it seems that there is, you know, a kind of a shared untold knowledge that maybe Ringdown was visible in the first event and in a few others, but the truth is we really see clear, strong Ringdown signatures in many of the events, and specifically in 17 out of the 50 events detected by the LVC. So we are really into the era of population-based test of general relativity using these observations. And so from that paper, I just want to report one result, which I think it's very interesting, which is a bound on the deviations from the GR spectrum. So what you do is that you predict some frequencies, assuming a curve metric, so the frequency in the damping time, and then you add essentially a parameterized deviation, so 1 plus some parametric deviation, and then you want to constrain these deviations from the data. And we did this for all of the events, and then we combined them all together. And what we obtain is this probability distribution here, which peaks nicely around 0 and as an error of more or less plus or minus 35%. And from this, you can also extract a Bayes factor for the presence of any modifications to gravity. And the Bayes factor is negative, which tells you that general relativity is favored in this case. And there is an update of this measurement in a recent paper by Ghosh et al., so the AEI Potsdam group.
Sorry, Gregorio, this
Yes.
plot is made as an average over all the black holes, or?
Yes, exactly. So the thing you have to notice here is that this deviation doesn't tell you anything about the system. So it's just, of course, the frequency of each system will be different, but then you are essentially modifying them all in the same way. So this means that these deviations will depend on each black hole. And to combine them, you have to use what's called a hierarchical technique. You cannot combine them immediately all together. But yes, it's a kind of an average, a refined average over all the black holes. Yes, it's from all the events we detected.
Okay, okay.
So actually, specifically, this was done with the technique where only a few of them were available. So it's just few of them. It can be improved a bit with more events. But yes, it's essentially you have to take it as an average. Yes. Okay. So yeah, this result is interesting because it's a bound on the possible deviations that you can have in the spectrum you measure, and we spent a lot of time to do this, and we are very happy with this result. But now I have a somewhat provocative slide, which is, does this result pass the so what test? And what I mean by the so what test is that if I take a Gaussian mixture of theoretical particle physicists and general relativists, which are working on modified theories of gravity since 20 years, and they have they have their own theory, they work on Orava-Lifshitz gravity or whatever, then they see these results and they look at it and they say, I argue that a lot of them would say, so what? In the sense that if you show them these results, it's not clear what are the implications on a specific theory. because in the end, what we're really interested in is to constrain a specific theory of gravity, right? We don't care about any parametric deviations from the Kerr spectrum. We care about what are the implications on this theory and this other theory. At least it's not that we care, but a lot of people care about the implications on this specific theory. And the point is that extracting the implications of these results to a specific alternative theory is not immediate. This is not always the case. For example, there are some other observations, the graviton mass, for example, where this is easier in some way, but not for the Ringdown. So why don't we constrain specific theories? Because most theories are not proven to be well posed, or it's difficult to justify certain approximations or understand merger Ringdown. And it's also once you step out the comfortable shoes of GR, there is a huge amount of possibilities and of effects that you have to take into account, like isospectrality breaking, parity violations, additional modes, etc., etc. So the policy of the testing GR group has been to not consider specific theories for which a rigorous framework has not been established. But still, we are interested in doing so. And so a recent paper, which has now been accepted by PRD, in a recent paper, I tried to project these constraints on specific theories of gravity. And the trick to do this is to assume essentially perturbative, to essentially assume a perturbative expansion. So this was a framework introduced by Masselli et al. And if you do this way, if you do it in a perturbative way, then you have a consistent framework with which you can constrain specific modified theories of gravity. And so what you do is that you take your spectrum and you simply expand it in powers of the remnant spin, because the mass dependence is easy. You expand it in terms of the remnant spin, and once you do that, so this is just the remnant spin to some power j, and then these coefficients here are just numerical constants, which means that they are independent of the specific black hole you are considering. So you don't have to average anymore in some sense. And then only then you add deviations at each given ordering spin. So you add some deviation, but only at the, for example, to the non-spinning term, to the linear in spin, to the quadratic in spin, and so on. And now these deviations, where again, these numbers are also numerical coefficients, these deviations are proportional to some gamma factor. And this gamma factor is essentially proportional to the action coupling. So to the coupling appearing in your alternative theory action to some power p, which will depend on the class of specific theory you are considering, which I will go into that in a moment. And so this framework, and another advantage, of course, is that now you are in a perturbative setting, so you can use GR values for the remnant mass and the remnant spin, because in general, in a generic theory, not only the spectrum is modified, but also the mass and the spin. And so there are several advantages of this framework, which is that it's applicable to large theories, to large classes of theories. It's source independent, so you don't have to make a refined average, as I called it before. You can just combine the constraint all together, and so you get optimal constraints. As I said, you can use the GR remnant mass and spin. And more importantly, there is a direct connection with the parameters appearing in the action, which is very interesting for constraining alternative theories. And so the consequence is that you are imposing more, essentially you're imposing more information. And so you need a much smaller number of signals or smaller SNR to detect any modifications from GR prediction. Sorry, I will take a sip of water. So some of the classes of theories to which you can apply all of this is, for example, P equals Z. The case of P equals 0 would be scalar tensor theories or Einstein-Adler, so Lorentz violating gravity. Then for P equal 2, you have a dark photon. For P equal 4, you would have, for example, some well-studied case of quadratic gravity. And for example, in dynamical and Chern-Simons, you can easily understand what's the coupling parameter I'm adding to the Ringdown. So I showed before this coupling parameter gamma, which was proportional. I showed this gamma parameter, which is proportional to L. And this L, essentially, you have to think about it as an effective field theory length scale. So below this L, the effects from the new theory will start to become important, while for distances very much larger than this L, which is dimension of a length, then the modifications from the alternative theories are essentially not important, and you recover GR. And it's exactly what happens here. So that the L in the dynamical Chern-Simons theory is essentially the length scale at which the modifications from the interaction with the scalar field start to become important, and of course the higher curvature terms. And for P equals 6, you have classes of effective field theories which are compatible with the fundamental principle of locality, gauge invariance, etc. And so now I will show in turn the results on each of these theories, and on each of these theories. And for example, for P equals 0, you have these results. So you can constrain the fundamental frequency deviation with a precision which is plus or minus 5%, which is much tighter than what I showed before. And you have a Bayes factor which tells you that GR is strongly favored. And here you see the probability distribution, which of course gets larger if you start to consider many more corrections to the spectrum. So since the corrections are perturbative, you can start to include more and more correction to the spectrum. But of course, the larger is the number of the additional parameters you include, the wider is this distribution, because you have correlations with other parameters. And so it's a good improvement with respect to the LVC parameterization, and you also need less signals to detect a violation. And then for the results on quadratic gravity are, I show them as a constraint on this length scale of the theory, which has to be smaller than 35 kilometers, which is shown here. And this has to be compared, for example, to constraints on dynamical Chern-Simons or Einstein-Maxwell U, where you had a constraint respectively of 30-50 kilometers or between 6 and 10. So you see that the constraint is quite competitive in some cases and more or less on the same order of magnitude in some other. And I also wanted to point out a result which I have in this paper, which is the best non-perturbative constraint on Einstein's scalar-Gauss-Bonnet, which can be obtained if you assume that 1908-14 was a BBH. So it tells you that the length scale should be smaller than 3 kilometers. And this is completely independent from the rest I'm doing here. I just wanted to notice this as an aside. And you can do the same on the effective field theories, which are, in my view, probably the best motivated framework in which you explore these deviations, and you get a constraint of 42 kilometers, which is much better than the previous best bound, which was obtained from gravitational-wave in spiral. And in the language of the paper which obtained this constraint, which is by Sennett et al., so the Buonanno group, we are now probing the finite size effects of this. So we're not probing the long range effect which we're probing with the spiral, but the finite size of the black hole. And that's it. On similar, I just wanted to advertise this paper where you on, let's say, similar grounds, you can extract constraints on the on the conjecture that tells you that the area of the black hole should be quantized. But I don't have time, so I won't go through this. While I will, if there are no comments or questions, I will go to, or of course, if you want to have them later, I will go to describe a recent result which we put out last month, which is a bound on the information emission rate of black holes that you can extract by analyzing these binary black holes. And so that to understand what this bound is and why do we care about it, so the bound stems actually from a quite simple question that one can ask, which is, what is the maximum rate, respecting causality, of course, at which you can at which information can be lost by a perturbed thermodynamical system. So this is a completely generic question that you can ask. It doesn't depend on black holes or on gravitational systems. And the result on a generic thermodynamical system was derived by Bekenstein in 1981, where he derived that the average rate of information, the maximum average rate of information, is essentially proportional only to this delta epsilon, which is the energy of the signal in the receiver's frame. So it's just proportional to the energy of the signal times some numerical constants. These are quite simple results, and it's remarkably simple given the complexity of the problem in general. And then Hod took a step forward by assuming entropy equal information, and which gives you this formula here. And I'm approximating the derivative by some relaxation timescale of the system. And then if you assume the laws of black hole thermodynamics, you can derive essentially this form of the bound. So we are translating a bound on the information emission of a generic system specifically for a black hole. And for a black hole, this omega I is the inverse of the relaxation time, which appears here. And so essentially what this is telling you is that the relative ratio of the radiative contributions, the radiative modes, divided by the thermal fluctuations of the system have to be smaller than 1. And for a black hole, this is the Hawking temperature of the system. And this is a nice result, but one would ask why should I be interested in this? So the interesting point of applying this to black holes is that black holes can have very large values of this bound, and they can also saturate in the limit of extremal spin. And this tells you that black holes are essentially the fastest dissipating macroscopic objects in the universe. So they are dissipating information. They are relaxing towards equilibrium in the fastest way possible. And this is this could appear like a trivial point, but it's really not trivial from a theoretical point of view, because classical systems are not expected to saturate this kind of bounds, while quantum mechanical systems are. And because the bound saturation is usually a universal behavior close to quantum critical points. So if you have a system which is undergoing a quantum phase transition, you would expect a saturation of this bound, but not for a classical system. And actually, this stemmed a lot of interest into trying to understand whether black hole perturbations could be treated like classical thermodynamics, or if they should be treated differently. And Professor Sachidev also pointed out that this similar bounds were one of the main, let's say, main points from which they started to think about concepts like ADS-CFT. So the connection between these strongly interacting, these gravitational systems and strongly interacting condensed matter systems, essentially. And it's also that there's also a connection to the viscosity entropy bound, which is a similar bound that you find in high energy physics. And of course, it's also interesting to test because you have the combined prediction of GR, information theory, and quantum mechanics, of course. And so that's what we did in this paper. So we measured, we extracted from the measurements of LIGO-Virgo a bound, a measurement of this bound. And so what I'm showing here are the probability distribution on this H parameter, where H is defined as the ratio of the two contributions that I mentioned before. And so in black, you have the prediction that would come from GR, while in red, you have our measurement, which is broad, but it nicely agrees with the prediction. It peaks close to the prediction, and it's safely below 1. And
Gregorio,
yes.
What is the I in the omega I? I missed.
Yes, so I means inverse. So it's omega I is the inverse of the relaxation time. So the ingredient.
You mean this is the smallest quasi-normal mode, the first quasi-normal mode?
Essentially, yes. So what you do is that you measure. You don't identify it specifically with the quasi-normal. So okay, I would be the imaginary part essentially of omega. So it's the inverse of the damping time. You don't have to identify it with the dominant quasi-normal modes, because these you can derive this in an agnostic way by measuring the relaxation time of the system. But yes, in practice, it's close to the inverse of the damping time of the fundamental quasi-normal mode. So yeah, the ingredients to extract these measurements are a measurement of the relaxation time of the system and the measurement of the temperature. So the relaxation time, we can derive it essentially by analyzing the post-merger emission, while the temperature, you can derive it by assuming that this was a Kerr black hole.
Okay.
Okay. And yeah, so as I was saying, the uncertainty mostly comes from this relaxation time measurement, so on this omega I, and it's in close agreement with the GR prediction. But one looks at these results and it doesn't seem very surprising in principle. So it's not, it's a probability distribution. It peaks below 1, and that's it. But the point you have to realize to understand, you have to realize is that such large values of this distribution are really a reflection of the extraordinary properties of black holes. Because if you would do this measurement for a system which you have in the lab, you would find an information emission rate which is 11 orders of magnitude larger smaller than this. So the fact that this distribution does not peak to 10 to the minus 11, but peaks to values close to unity is really a remarkable property of these systems. And in the end, the root is in the fact that we have a system which is 100 kilometers wide, so as big as Tuscany, which is relaxing towards equilibrium in just a few milliseconds, which is quite impressive. And of course, we wanted to do this for the full black hole population, and we did it by. Oh yeah.
Can I have a question, Gregorio?
Yes, yes.
If you go back, so what is driving your prior?
Okay, so you have to. That's clear. Okay, that's a good question. So the prior is driven in this first plot. The prior is driven essentially by the LVC priors on the component masses and component spins, and on a uniform prior on the relaxation time. But then we redid this in the hierarchical framework by reweighting with a uniform prior over H, and you still get consistent results. So, but yes, the prior is in the first plot, it was determined by essentially the component mass and spin priors. Yep.
Okay, thanks.
Yeah, what it's telling you is that for standard systems, you would really not expect a violation of this bound. That's what it's telling you for black holes. Yeah, so I won't go through the details of here because I'm running late, and I wanted to go through the last topic.
Sorry, and how does depend omega I on the constants of the black hole?
It doesn't. So omega I is just the inverse of the relaxation time of the black hole. So in this analysis, you're just essentially measuring how long the system takes to relax. You're not imposing any specific prediction of GR. You can impose it, and you would get the black line, essentially, the black distribution.
Okay.
But of course, roughly you would expect it to be larger if the mass of the system is so. The larger is the mass, the larger you would expect the relaxation time. So the smaller would be the omega I, essentially. But in the end, this ratio only depends on the spin of the system, because you have a simplification of the mass between the relaxation time and the temperature. So in the end, this just depends on how fast the system was spinning, or how much electric charge the system would have.
Yeah, but in principle, you could calculate the value theoretically.
Yes, you can. Yes.
Yeah. Okay.
Yeah, it's more or less this black prediction. Yes.
Yes, but it has to be related with. I mean, you could calculate it alone as a function of the temperature and the spin of the black hole.
Yes, of course.
Right. Okay.
Yep.
So, and do you know that function?
Sorry.
And do you know how is that function?
Yes, it's well, if you assume that this was a quasi-normal mode, it's essentially a rational function of the spin on top and the usual expression of the Hawking temperature in the bottom.
Okay.
Yep.
Thank you.
All right. Yeah. So then we redo this on the full black hole population. You have to use what's called the hierarchical Bayesian analysis to do this, because you cannot combine trivially the constraints altogether. But the full population, both in a modeled way and in a more simplified way with an average likelihood measurement, they both confirm that the black holes respect this bound, essentially. Okay. And finally, in the last few minutes I wanted to show some preliminary results we got with some collaborators from England, Oscar Diaz, Godasgar, Johnson McDaniel, and Jorge Santos, together with our usual crew, which is me, my supervisor, another PhD, and John. And so this is trying to answer the following question. So in LIGO-Virgo measurements, we always ignore the presence of an electric charge in the black holes. So can we relax these assumptions, and or in general, what can we say on Kerr-Neumann black holes from these observations? So Kerr-Neumann black holes are just the usual Kerr black holes endowed with a U1 charge, which could be an electric charge, but it doesn't have to be. So this result is preliminary. I hope we will put out the paper in a few weeks, but take it with a pinch of salt. All right. So what are the motivation to test Kerr-Neumann black holes? So there is a motivation also for tests of GR, which is that the deviations from the Kerr metric are known for arbitrary spin in this case. So this means that you have a well-posed, consistent framework with which you can modify your standard scenario, which is Kerr. And this is a valuable test for beyond GR effects to understand if we can capture beyond GR effects, which are consistent and well motivated without any perturbative assumption or similar. The astrophysical charge is usually expected to be negligible, and this relies essentially on the charge to mass ratio of the electron. So there are mechanisms like vacuum polarization and electron positron pre-production which prevent a black hole from getting charge. Essentially what happens is that the system has a curvature which is so large that when it acquires a little bit of charge, it polarizes the vacuum, and so it starts to attract charges from the opposite side. And there are also more mundane mechanisms like neutralization from surrounding materials, of course. But this is helpful to constrain some non-standard scenarios, which are mini-charge dark matter, which could give you this kind of signature, also magnetic monopoles, scalar tensor vector gravity, where gravity is mediated by a vector field, and a topological induced charge. So all of these scenarios can be reduced to the Kerr-Neumann, can be incorporated in the Kerr-Neumann metric for what concerns these modifications. And so we can investigate all of this by investigating the Kerr-Neumann metric with these observations. And so how do you predict the spectrum of so we want to do it with the merger Ringdown. How do you predict the spectrum? This has been a long-standing problem because in Einstein-Maxwell, the Ringdown equations are not separable. But it was recently solved by our collaborators, pinning on Chandrasekhar's work, and they could predict the spectrum for arbitrary values of the spin and the charge, and they proved the stability, the linear stability of Kerr-Neumann up to very large values of extremality, which was a very interesting driving point for them. What they found is that, first of all, the modes which are connected to Schwarzschild, so the ones which go back to the Schwarzschild value once you put the spin and the charge to 0, are the ones which dominate the spectrum, which is not a trivial result. And the other thing is that it was missing let's say an extensive public tabulation of these results. So what we did is that we started to extend their solutions, and we computed a large number of numerical solutions. So we tabulated the quasi-normal modes for the most dominant modes that you expect in a bi-black hole coalescence. So here would be the black dots on the plot. In reality, here I'm showing only the validation set on which we trained our fits, but the actual training set, so the full set that we computed, was 10 times larger than the number of points you see here. So it was a very extensive tabulation. And then after that, of course, we want to build an analytical representation, which we did by using rational functions. And here you can see the red net is the rational function, which actually captures the spin and charge dependence quite well. The residuals are essentially at the level of 0.1%, which is comparable to what you have for Kerr black holes from the fits. And in the shadow here is again the residuals plotted in the different parts of the parameter space. And of course, the highest residuals are towards the extremal limit, because the extremal limit is actually special in this case, and you have to treat it in a specific way. And our collaborators are actually investigating this at the moment. And the thing I wanted to mention is that we use the Bayesian fit, which allows you to have errors and correlations and so on, which is nice. And so once you have the spectrum, you just build a template by superimposing damped sinusoids, and this is the result. So the Kerr one is the yellow, and the template where you add the charge tends to have a higher frequency and a longer damping time. We ignored electromagnetic driven modes, which can arise in these situations, because numerical simulations seem to show that they are negligible. But of course, we want to compare directly against NR in the future to understand if this is really the case. And then once you have a template, you just run it on all the events, and you try to measure the charge. Unfortunately, here you see this the distribution on the charge to mass ratio, which goes from 0 to 1. And the prior is the bluish line that you can see here, while all the events are these purple pinkish lines, histograms. And you see that essentially all the events give you back the prior that you put. The prior is a bit funny because you have to impose that these black holes are non-extremal. And in the case where we also have charge, it's a combined constraint on the charge and the spin. So usually for Kerr black holes, their dimensional spin has to be smaller than 1, otherwise you violate causality. In this case, you have to sum in quadrature the charge and the spin, and they have to be smaller than 1, which translates to this funny prior. But the point is that there's no direct measurement possible, and the Bayes factors tell you that you cannot discriminate the presence of the charge. And the reason for this is essentially a very, very strong spin and charge correlation. So here I'm showing a measurement on a single event. This is the spin and charge plot. It's a probability distribution on these parameters. And so the light blue line contours the 90% credibility region, which you see is very broad. And what you can also see is that you are not excluding any value of the charge. So this credibility region goes from very high values of the spin compatible with small charge, but also very small values of the spin compatible with high charge. So these parameters are strongly degenerate, and you cannot disentangle between a large value of one and a smaller value of the other. And so to break this correlation, you would need information from the previous phases of the coalescence or some prediction for the amplitude, which we don't have at the moment. But there is another way in which you can manually break this correlation, which is just to say, okay, let's try to do a null measurement, which is telling you that, okay, the LVC has measured some remnant mass and remnant spin for these parameters. What is the maximum amount of value which is compatible with the LVC measurement? And so it is a kind of null test, and it just tells you, the maximum amount of charge which is compatible with current observations. And in this case, you obtain a bound which is more or less 0.33. The maximum value is 1 here. And so the prior again is the blue, and these are all the curves for the different events. And 150914 is still the strongest constraint here. So you can get a quite good constraint. Of course, you're making a strong assumption, which is kind of a null test of this prediction. But then once you cannot measure it with current observations, so these are the observations we already got, and also you have no evidence from Bayes factors. The next question is, can we discriminate the presence of the charge with future observations? And so we did what's called an injection study. So we simulated signals with future upgrades of the current detector. So these LIGO-Virgo data at the sign sensitivity. And what we found is that you can actually measure the charge only for very high values. So even at the sign sensitivity, if the charge is smaller than 0.3 or even 0.5, you cannot really tell anything. But only for very large values of the charge, you can start to measure something. So these either for third generation detectors or for LISA measurements to be confidently discriminated. Unless, of course, we start to build coherent templates where you start to have these effects also in the spiral and merger. And yeah, so that was it. I hope I convinced you that black hole perturbations now have unquestionably transitioned from a mathematical problem to an observational reality, and that they are useful tools to test modified theories of gravity, investigate the nature of these compact objects, so and understand if we are really seeing black holes, and of course to explore the black hole's remarkable properties, and finally to search for signs of new physics like dark matter particles, which could give rise to specific effects in these observations. And that's it. Thank you for your attention.